So far we have been transforming our shapes, and now it's the time for us to transform some of our functions. So how does that work? Well, let's say that I have a function y equals f of x, right? And let's study three different transformations and what would be the results of those. So the first one, let's work with f of x plus k. And here, k is, let's say, an integer, okay? And k is different than 0. It didn't have to be an integer, it could be a real number, but for now, let's assume that it's an integer. Okay, so f of x, the function that we had before, plus some constant, some value, some integer. Okay, the other second kind of transformation we're going to look at is f of x plus k. So I'm not adding just some constant to the final value of y, I'm actually adding k to the value of x, and we'll see what that actually does. And the last one is, well, multiplying everything by a factor, f of x, right? So we have here f of x plus k, I'm adding some constant. Here it's f of x plus k, so I'm adding some constant to the value of x, and here I'm multiplying everything by a factor of k. Now it seems like a minor detail, but k has to be different than 0. Well, otherwise, here we wouldn't have any difference, right? If k was 0 here, it would be just our original function. This one the same. And the last one, if k is 0, well, you're going to have y equals 0 for any function, right? You can multiply this by 0 by anything and you get 0. So k, let's assume that k is different than 0. So let's take a look at those examples here. So I've got the same line, it's just a line, a very simple example here. And let's see, what would happen if I added some constant? Well, each of those heights would now be a bit higher, right? If this was 1, then all of my y values would be whatever they were plus 1. So I'm moving my function up. Right, so we would basically move this line up by k, and then this would be our f of x plus k. So if this was, let's say, 2, then I would just shift my line. I would basically move it, slide it upwards by a factor of k. Now, what about this second example here? Well, I'm adding k to the axis. So my function is being shifted to the left. For example, let's say that I had my y equals f of 0, right? If I'm doing f of x plus k, now this would be f of k, right? So I'm going forward a few units. So my function is actually being slided to the left. By negative k, right? So this would be, well, k, but since it's negative, it's going to the left. And this is our f of x plus k. Right? The last example here is when we multiply by a constant. So what's going to happen here is that we're going to shift this gradient. So for example, on this line here, we could try to calculate the gradient. This was up to scale. We could just get rise over run, right? Or simply, if our function is in the form ax plus b, which is the equation of a line, this is our gradient, right? And now we're multiplying everything by some constant value. So our function now is going to be with a different slope. So this would be k f of x. Now, most importantly, there will be an invariant point here on the x-axis, right? There will be a point here where this function would meet 0, and both functions, both lines, they will still have that same 0 point. There is another situation here which is reasonable to mention. It's when, for example, this k is negative. When this k is negative, your slope now will shift downwards. So if, for example, k is simply -1, I would have exactly the same line. Well, it's not exactly the same one, but let's assume that this one is exactly the same one. This would be minus f of x, right? That's exactly the same function. Here k is -1. I'm just flipping, I'm just mirroring my function horizontally, right? Sorry, towards the horizontal axis. So this is a summary of what happens when you're transforming functions, right? So our original function here is y equals f of x. Then it's going to map into f of x plus k. We're going to have a vertical translation, 0k. This is our vector here, right? Now, if you do f of x plus k, then it's a horizontal translation, and then you're just moving to the left. That's what this negative means. And, sorry, if you have k f of x, then it's a stretch, and you've got an invariant x-axis. Remember, there will be a point that's not going to change. That's your 0. And the scale factor will be k. If k is -1, for example, the scale is 1. You're just taking the mirror. So let's see some examples. Right, so consider this function f of x equals half of x plus 1 on separate sets of x's graph. So the first one, y equals f of x, and y equals f of x plus 2. So for letter A, let's draw some x's here. Alright, x and y. Now our function is half of x plus 1. So this is our vertical, right, intercept here, y-intercept. So this point, let's say, this is 1. Now, since our gradient is half, that's rise over run, so that means that I'm going 2 forwards and 1 up. Right, so this is a point of my function, and now if I go 2 forward, I would simply go 1 up. And since this is a line, now I would be able to, that's enough for us to represent a line. That's f of x equals half of x plus 1. Now, if we're doing x, f of x plus 2, it should be a horizontal translation, right? Negative k and 0. So removing 2 to the left, right? 2. So, for example, this y-intercept, which was 0, 1, now it would be -2 and 1, right? Because it moved to the left. This point here, which was 2, 2, now it's going to be 0, 2. And that's our no line. Now, if you ever forget those things, you can always try and do f of x plus 2. Right? What would be the equation of this no line? Well, your f of x was half of x plus 1. Now you're doing plus 2, so x here would be plus 2. Plus 1. Right? And then that's half of x. 2 here, and half, that would be plus, x. Plus 1, plus 1. So that's half of x plus 2. And that's our new line, right? So you could get to the new equation. This is just a way for you to get to it faster. What you could also do if you forget is make a table. You can always do this if you forget how to plot a function. You can get some x and y's, right, and try it out. For example, here when x is 0, that's my f of x. So let's put this in a better way. So let's do x, f of x, and f of x plus 2. So if x is 0, my f of x is 1, and my f of x plus 2 is 2. Right? You can just put the values in. Right? What about 1 here? Well, when this is 1, my f of x was half. Right? And my new function, oh sorry, that's 3 halves. Right? It would be this point here, right? 3 halves. So it's 1 and a half, 1.5. And this one would be 5 and a half. You could also do negative 1, right? Oh, computers. So negative 1. So if I do negative 1, f of x, my original function at negative 1 would be a half. Right? And what you could do here, there's a negative 2 would be a better value, but let's do negative 1 first. So negative 1, our function of x plus 2 would be 3 halves. Right, you can do this table, and then you can plot the function. For a line, you only need 2 points. Now the best points would be this and the last one, because negative 2 of f of x, if you look at this line, since our gradient is half, it's going to be 0 when we reach negative 2 here, so that would be 0. And this one, f of x plus 2, it would be 1. So you can just plot the line with that data as well, and you can find out your transformations as well in well, whenever you forget. Now, what about the other examples? So let's do letter B. I've got y equals f of x, and I want to transform into f of x plus 2. So this is quite obvious. That's the easiest for us to see, right? Because that's x, that's y. Our original function is our half of x plus 1, so that's a gradient of a half. So that would be 1 here, the height would be 2, and this would be 2. That's our original function f of x. Now for every point in this function, we will basically have a 2-point higher, right? It's going to be 2 units above. So if this point was 1, now it's going to be 3. Right? If this point here was 0, now it's going to be 1. Now this graph's not quite good. Alright, now it looks better. So this is our function. Now what if I'm going to points above? So this point here was 2, now it's going to points above, it's going to be this one. This was 1, now it's going to be 3. This was 2, now it's going to be 4, and that's our new line. Well, if I manage, yeah, there you go. Right? That's our f of x plus 2, and we have basically shifted up by a factor of 2. The vector which describes our transformation is 0, 2. Why? Because every point of this function has moved 0 units left or right, So there was no change on the x-axis. However, all of the points have shifted, have moved, have translated upwards by 2 units. So there you go, 2. So the vector, our transformation vector, or our translation vector, would be this one, okay? Our translation vector. In the previous example, our translation on the letter A here, our translation vector was -2 and 0. Why? Because we moved 2 units to the left and we did not move up or down, right? So those numbers, they come from here, right? So it's easy to notice. Okay, so letter C now. I'm doing 2 times, I'm multiplying my function by 2, so scale factor 2. This point here will be our invariant point because it's 0. If I multiply 0 by 2, by k, by anything, really, it's still going to be 0. So this point will not change. And what's going to happen here is, if we make this value larger, if we multiply this function by something which is larger than 1, we'll have a line which is steeper, which is this case, right? If we had a k which is between 0 and 1, then we would get a less inclined slope. If we had a negative k, right? So if this is less than 0, then we will mirror this against the x-axis, right? And it's well, if k is exactly -1, it will be exactly the same line but just flipped. If it's, let's say, -2, you not only mirror it, but you also stretch it by a factor of 2. But anyway, in this case, this point was 1, this here was 2. Now, since we're basically multiplying everything by 2, this height was 1, now it's going to be 2. This height was 0, it's still going to be 0. With those 2 points, we can already draw our line. But we could get some more points. For example, when this function is 4, I will have here 3, right? And now it would be 6. So if we just follow those points, that would be our new function, 2f of x. So every point here, it should be twice what it was in the previous function. So this was 1, now it's 2. Let's say this was 2, now it's going to be 4. This should be 4, right? This here was 3, now it's going to be 6. And there you go. Now, last example, letter D. It's exactly what we were talking about before. It's a -f of x. So this was 1, 2, and 3. So we're going to get exactly the same points. So this was 2 and this was 4. Now, when x was 2, my function was at 2. Now it's going to be at -2. When I'm at 4, my function is 3. Now it's going to be -3. Now same thing here. It was 1. Now it's going to be -1. So this point is there. This point is there. This point is there. This is our invariant point. And you can see already the points that would be connected for us to get our line, right? So this would be -f of x. Our factor now here is -1. And that's it. That's it, really. If you need any help, you can always use a calculator.